today is the 8th of September, and we are continuing our trek through Chapter 2, which talks about stress and strain. So we're going to talk about a couple of relationships, but we are referring back constantly to this diagram, the stress-strain diagram, and we've talked about normally behaving materials will have a straight line, a constant slope within the elastic region before we have rupture or yield, and that this is the area where we are going to be concentrating our attention in this class. And for the most part, when you become engineers and you're practicing engineers, if you're designing, for the most part, things are designed within the elastic region. So sometimes if I were feeling clever today, I don't know if you guys remember, or if you've ever seen, but back in the old days when people thought the earth was flat, although some people still think the earth is flat, I have come to find out. I don't. But anyway, when they would draw maps, they would just kind of put an edge on where they thought the world ended, and then they would put pictures above it. It would say, if you go beyond here, there be dragons. So maybe that's what we should think about, is that if you go beyond here, there be dragons. So this is the part of the world that we're the most interested in right now. Well, we know that the slope of a line, we referred to this as the modulus of elasticity, or Hooke's modulus, and the slope of the line is equal to the change in y over the change in x. And since this runs through 0, the numerator is sigma minus 0, and the denominator is epsilon minus 0. So we can just eliminate that, and we can write this particular equation, and this is referred to as Hooke's law. So what it tells us, and we can rewrite it a little bit, and we can say sigma is equal to, in other words, normal stress, is equal to the modulus of elasticity times epsilon, which is another form of Hooke's law. And what that means is that while we're in the elastic region for a normally behaving material, that we will have a relationship, a linear relationship, and that it's governed by the modulus of elasticity. Now, the modulus of elasticity, like we talked about, is a characteristic of, the graph itself is a characteristic of a material, but also the modulus of elasticity. It's very well defined. And in the back of your textbooks, there are pages and pages of data about different material. And one of the pieces of data that they give you is that modulus of elasticity. So I'm going to put up here just so that you can see. This is Appendix B of your textbook, typical properties of selected materials used in engineering. You see that we have types of steel, cast iron, aluminum, copper, some alloys, and then some kind of odder things down here, more odd things down here. And we have a factor here called modulus of elasticity. And if we have units of PSI, the modulus of elasticity is often a very huge number, because remember, modulus of elasticity, the bigger it is, the less stretchy a material is. So what that's really saying is that you have to put a lot of stress on a material to make it stretch at all, which makes sense because we don't design with silly putty, right? We design with steel, and we design with wood, and we design with cast iron. So the values are shown here. They tend to be 2 digits times 10 to the 6 psi. We'll talk a little bit about modulus of rigidity later on, but that's related in a way. And then we have some other, the coefficient of thermal expansion. Remember we talked about sidewalks, the expansion cracks in sidewalks and so forth, how materials will expand in temperature. This is a very small number, 10 to the minus 6 per degree Fahrenheit, which is also, I mean, you wouldn't expect concrete to double its size if you increase the temperature by 100 degrees. It just increases a little bit, but it's still enough to mess up your sidewalks. Okay, then we have the next page. I'm not going to go through this anymore, but just to show you where to find it, Appendix B, this is in SI units. So here the modulus of elasticity is written in gigapascals. If you remember, a giga is 10 to the 9th. So this is a whole lot of pascals, isn't it? So it's a big number, once again. I also found out something strange. If any of you watched the old movie Back to the Future, remember it talked about gigawatts of electricity? It's actually it's an okay pronunciation for that unit. Although it sounds weird, but I always thought it was giga and thought they were just mispronouncing it. But it's okay to say giga. It's an officially approved pronunciation. I will not be saying it in here unless I make a mistake. However, so all right. So we had just talked a little bit about repeated loadings and failure, and we talked about fatigue. We talked about creep, and we talked about slip and creep, which are just repeated loadings or age that cause a material to not behave the way that we expect it to. Here in page 66, there is a drawing that describes what happens to material under permanent loading. And if you notice, here's our run home to what we know. The line A to B indicates, let's see if I can come in a little bit closer on that. Okay. The line A to B shows us that elastic behavior. Whatever this material is, this is a mild steel. What happens is we pull on it until we exceed the yield, and we have this highly ductile type of behavior. What happens then here from C prime to D prime is we are unloading it. In other words, we are removing sigma, and we see that it goes back in size, but we have this distance between A and D prime, which is now we have no loading, but the material is longer. Okay, that's referred to as a permanent set. In other words, we have exceeded, we've yielded that material, and now even though we take off the loading, we still have a lengthening of the material. The material is significantly different on a structural level at this point. It is not as reliable. This is like where the solder necks and gets hot. Okay, so you quit pulling on it, but it's still skinnier and it's still longer. So then what we do to see if we can get rid of that permanent set is we actually put it in compression. So below this line, because this is sigma, here's sigma 0, below the line we have sigma negative, which is compression. So we put the material in compression, it follows some other weird curve, and then we remove the compression and it comes back to K prime, which means we still have a permanent set. But because that material was altered structurally, we still have a permanent set, but now it's different. So this is the difference between the permanent set at 0 before and the permanent set at 0 after we compress it. And you can see neither one of them amounts to 0 in terms of the elongation. And then if we add sigma back in, it just fails. It just turns into string and fails. So from C to B, it's sort of the same thing, except for we don't go this far out, and we take on a permanent set from A to D. We put it in compression. It actually goes back to an elongation of 0, and it will compress to some other value J, and when we remove it, it will come up to K, and it will take on a negative permanent set. So here, this actually indicates if we do this with our load curve, that we will take on a negative permanent set, meaning that it shortens permanently after being subjected to a tension and a compression cycle. So once again, here's the dragons, right? This is where we're interested right here. This is where design happens in its finest form, in its most definable form. And like I said, it's not that we never design in the weird place, but in this class, we're not going to design beyond the elastic zone. You just need to know where that occurs and not let it happen to you. All right, so let's take a look at this formula and let's see what else we can do with it. I'm just going to write this in the form that your authors write it. Now, this is always within the elastic region. Does this equation have any applicability after we leave the elastic region? I'm kind of leading you to the answer. No, thank you very much. In other words, this only works to here. If you're up here, oops, oh yeah. No, the other way. If you go beyond this point, this equation is not valid. The equation is valid only in the elastic region. But let's talk a little bit about some things that we know. Well, we know that for normal stress, sigma is equal to P over A. And we also know that epsilon, because it's the percent, is equal to the amount of stretch over the original length of that object, whatever it is. So if we solve this equation for del, we can say that del is equal to PL over AE. And this just gives us a dimensional equation, just a little bit different form. These are both useful, but they are both valid only within the elastic region. Okay. And this is actually a very workable form of the equation. And one of the things that we can do is that if we have a composite member, if we're pulling on something like this is an example 2.1. If we take, let me ask you this question. If we take the amount of stretch of this object when we pull on it and the amount of stretch of this object when we pull on it, will that be equal to the total stretch of the total bar? What do you think? Yes, absolutely. So if we take del 1 and add it to del 2, we get del total. Okay? This is important because sometimes we need to know what the total deformation is, or sometimes we can use a total deformation in order to find things that we don't know, and these are called statically indeterminate problems. What I mean by that is, let's say that we have a structure like a column that's constrained. We have a wall and we have a floor. And if we pull on it, we know that the wall or the floor is going to push back, and we know that the ceiling is going to push back. We may not know how much this expands and how much this contracts, but what do we know about the sum of the expansion and contraction of those two?
0.
Yeah, exactly. Del 1 plus del 2 here equals 0. Okay, so this is called analysis by deformation, and sometimes we can think of it as being, well, the type of problem is called statically indeterminate, which means we can't really tell what the reaction is going to be at the ceiling or on the floor based on statics, because we only have one equation, but we have two unknowns. However, since we know something about the deformations, even though the problem is indeterminate or unsolvable from a statics point of view, we can use the deflections in order to solve the problem. All right, so having said that, I'm going to do a couple problems for you. What do you think? And then you guys will get to do some problems, which of course is what you're really excited about. I know for a fact. Let's take a look at problem 2.1 in your textbook. And if you don't have your textbook in front of you, I will, let's see, this is too easy. And well, let me cover a little bit more material before I do that. Then it won't be too easy. Hang on. Just a second. You laugh at me. There is no such thing. We like easy problems. There you go.
Cover more material and the problem gets harder.
Yeah. Oh, no, it's okay. We'll just take a look at this problem. All right. We have a nylon thread. No, I really don't want to do this. I really want to do something that has a couple of parts to it, and then you can do 2.1. You can do 2.1 for homework, and it will be easy, and that will make you happy, because you can get 100% on it. All right. I want to find something with a couple parts. Okay. I'm going to do problem 219. Because there's a lot of stuff going on in 219, and it's going to help you a lot when you guys do 215. Right? Here's 219. We have a composite rod. I don't mean composite material, I mean a rod that's made out of two different sections. A composite material is something different, and those of you who are going to study mechanical engineering especially will become very knowledgeable and interested in composite materials. But I'm just talking about a rod made out of more than one chunk. Okay? So here I have rod ABC, and it's fastened to the floor, but it is not fastened to the ceiling. This portion of the rod is 0.5 meters tall or long, and this portion is 0.4 meters tall or long. Both portions of rod ABC are made of aluminum, for which E for both, E for everything, is 70 gigapascals. Or like I said, gigapascals if you prefer. Knowing that the magnitude of P is 4 kilonewtons, determine the value of Q, it's this force, such that the deflection at A is 0. Well, since this is a whole rod, that would be del total equals 0. That's the first part. And what is the corresponding deflection at point B? Okay, equals question mark. Right. So we have to find Q such that D total is 0, and if that is the case, then del at B is equal to what? All right, well, here's what we know. We know that if we pull on it with 4 kilonewtons and we pull down with some unknown force Q, that the floor is going to react, if Q is greater than 4, the reaction at point C will be upward. If it were less than 4, it would react downward, wouldn't it? We don't really know right now. However, I'm not even going to say that. So I'm just going to say, however, it's always a better idea to just draw this as positive mathematically, because then if it comes out to be the wrong sign, you know that you just reverse it and it's actually negative. Otherwise, you get into this idea of negative is a positive. And so if you're uncertain of a sign of an unknown, I would always draw it as a positive. All right, so the only thing we have here is for statics, we don't have any x direction forces. It's a column, so we can't really do moments. Everything is collinear. So we can say the summation of forces in the y direction is equal to 0, which tells me that positive 4 kilonewtons, I'm just going to say kilonewtons, so I don't have to keep writing Kn over and over again, minus Q plus Rc equals 0. Okay? And I do not know beyond this what those values are. So I have one equation, 2 unknowns. I need more equations. So that means that I wish to do analysis by deflection, which we just learned. And we're told that the total, the deflection total, has to be equal to 0. So what are the sums of my deflections? Well, my total deflection is going to be the summation of del from A to B. I shouldn't even write that. That's ridiculous. Plus the deflection from B to C have to equal 0. Because, in other words, whatever this deflects plus whatever this deflects is going to be the total. And I'm told in the problem that that's going to be equal to 0. Well, one thing you can see is that B to C, if I were to do that cutaway like we did in the first part, I put a line through it and I analyzed somewhere in the middle, that the way I have it drawn, this is going to be negative, isn't it? In other words, BC is in compression because the floor is pushing up, Q is pushing down, P is pulling up. But with my directional stuff, this looks to me like it's going to be deflected in a compression sort of a way. But here on A to B, what about that one? When I cut away here, it's in tension. So this should elongate. And the way I have it drawn, this will be a negative. All right, so let's think about what that means. On the last problem, when I rewrote Hooke's law, I found that del is equal to PL over AE. So I have PL over AE in part AB minus PL over AE in part BC, sum up to be 0. Now these are not the same P's, and these are not the same L's, and these are not the same A's. But E is the same because we're told that the entire thing is made out of some substance, an aluminum, that has a modulus of elasticity of 70 times 10 to the 9th gigapascals, or gigapascals, right? So what is my P in AB? Well, that's just going to be the 4 kilonewtons, isn't it? And I'm going to go ahead and write out my units because I just want you to see how they come out. My L of AB is 0.04 meters. The area, it's a circle, or it's a cylindrical structure, and we're told that it's 20 millimeters in diameter. The bottom part is 60 millimeters in diameter. Now, the first thing I would recommend to you is if you're using SI units, first of all, I would recommend to you to show everybody what you're doing. That would work. I would change this immediately into meters in order to avoid unit problems, and similarly here. So the cross-sectional area of a circle is pi times d squared over 4. And then my modulus of elasticity is 70 times 10. Sorry. It's 70 gigapascals, so it should be 70 times 10 to the 9th pascals, which is a Newton per meter squared. Okay. If I take that and I subtract my P here, well, think about this. The way I have it drawn, P here is going to be 4 minus Q, isn't it? I don't know what it is, but my response here is going to be 4 minus Q. My length is 0.5 meters. My area is pi d. A millimeter is 10 to the 3rd. Boy, I've been on vacation too long. 10 to the 3rd meters squared over 4. And my modulus is 70 times 10 to the 9th Newton per meter squared. And those two things added together equal 0. Okay. All right. Now here's something interesting, just mathematically. When you have one thing equal to the one thing minus another thing equal to 0, I can just pull this over to the other side as a positive, right? And so I can get rid of this and just do that. And what's really cool about that is I then have one equation with one unknown. And I can cancel out anything since I just have one term on one side and another term on the other side. Anything that is exactly the same and multiplied through can be canceled out. In other words, pi cancels pi. 4 cancels 4. 70 times 10 to the 9th cancels 70 times 10 to the 9th. And I'm left with a somewhat simpler equation. I have 4 kilonewtons. It'll be simpler again in a minute, but I didn't want to do this all in one step. Times 0.4 meters divided by 20 times 10 to the negative 3 meters, quantity squared. And these units also are gone, aren't they? Equals 4 kilonewtons minus Q times 0.5 meters divided by 60 times 10 to the minus 3rd meters, quantity squared.
Can you explain just real quick the 4 kilonewtons minus Q?
Yes, absolutely. All right, goes back to our drawing right here. In BC, this is just, I'm doing a cutaway. Here's BC. This is R sub C, right? And what do I have going on up here? Well, let's just do it that way. If I cut away, that means that my reactive force here is going to be R sub C, right? Okay, so R sub C, if I go back to my statics, if I solve this for R sub C equals Q minus 4, did I put my sign wrong? Oh, I did. Do you see what I did? So R sub C should not be Q minus 4 minus Q. It should be Q minus 4.
And that's your del of BC.
That is correct. And what we're saying is the del of AB equals the del of AC in order for the whole del to be equal to 0. Yep. Good catch. All right. So now what we can do, we can also recognize that we're going to get rid of some units. The meters and the meter squared are going to cancel because this will cancel this, and this will cancel this. And actually, 10 to the negative third squared cancels 10 to the negative third squared. So we're just left with 4 kilonewtons times 0.4 over 20 squared equals Q minus 4 kilonewtons times 0.5 over 60 squared. And we can solve this equation for Q, can't we? Okay. So what I'm going to have is, recognizing that Q is going to remain in kilonewtons, I'm going to just cross multiply. So I get 4 times 60 squared equals Q minus 4. It would be times 0.5 over here. So it would be divided by, hang on a second, 4 times, I forgot my 0.4 here. Okay, because it's 4.4, 60 squared. Then I've got 20 squared times 0.5 squared, or 0.5 not squared, and then just Q minus 4. So now we get to do a little bit of math, not too much, but we need to do our point, whatever that is. Let's find a calculator. So I have 0.4 times 4 times 60 squared. Okay. So my numerator, just because I have not much of a calculator here, is this. And then on the bottom, I have 20 squared times 0.5, which is 200, equals Q minus 4. Q then is equal to 4 plus 5760 divided by 200. That's 28.8 plus 4 is 32.8. So 28.8. So Q is equal to 32.8 in units of kilonewtons. Okay, so what does that mean? Well, this makes sense, doesn't it? I have to put quite a bit of compression on this larger joint in order that the compression here equals, not compression, but the shrinkage here equals the elongation here. Okay? All right. So continuing, the next part of the problem is, that's Q to get a total deflection. What is the deflection at point B? All right. So what we're looking at is just this part right here from B to C. What's the deflection at B to C? Well, it's going to be equal to the deflection from A to B, but we can just do this. Let's just draw BC. We have RC here. And we have Q acting down, and even though we have a P acting up. But if we do del is equal to PL over AE, the P that we're going to be experiencing is either 32.2 minus 4 or the R sub C, which would come out to be 28.8. So 28.8 kilonewtons times, and this is going to be negative, isn't it, because we're crunching it, 0.5 meters over the cross-sectional area, which is pi d squared over 4 times E, which is 70 times 10 to the 9th pascals, which is a Newton per meter squared. Okay, so we get negative, and let's do this, because this is in newtons. Let's write this as times 10 to the 3rd newtons so that we can get rid of those units. And then we have meters squared, canceling meters squared here, and we're left with meters. Do you think that's a good unit for a deflection? Yes, I do too. All right, so let's take a look at what the number is going to turn out to be. If we have 28.8 times 10 to the third times 0.5, on the top we get minus 14.4 times 10 to the third. And you know, it would be easier to just flip this 4 up and multiply it since it's in the denominator of the denominator. So that'd be 57.6. Negative 57.6 on the top, and then divide it by, if we do 10 to the third, negative third squared, that would be 10 to the negative 6. Multiply that by 10 to the ninth, we get 10 to the third on the bottom. So the powers of 10 go away, which is kind of nice. And all we're left with is 60 times 60. If you have a better calculator, you can do this more elegantly. Times 70 times pi. And so our denominator is 791,683.2. And if I multiply that by, if I divide the numerator in by that number, I get 57.6. And so my answer is the deflection is a negative 7.276 times 10 to the minus 5 meters. Or I could say negative 7.276 times 10 to the minus second millimeters. Now, does that make sense? I mean, it does. You don't expect this thing to, I mean, it's made out of steel, right? You don't think it's not going to deflect feet and feet or meters and meters. You would expect that deflection to be quite tiny. Okay. Do you guys have any questions about that? And actually, I'm going to go on and take a look at one other type. I don't know if I want to start this. I want to start this. I'm not going to give any homework from it. Your entire homework for tonight will be 2.1 and 2.15. And so I am a little bit behind in my lecture, but I think it's worth it because this will come pretty quickly. Let me ask you a different question, and we'll solve this on Monday. Let's say we have a different sort of a configuration. Let's say that if we looked at the top of a structure, we had a inner core of one substance, maybe steel, and an outer jacket of another substance, such as aluminum. So when we look at it from the side view, the way we would draw it is this, more or less, where we'd have that inner core and an outer jacket. Now, if we were to pull on this composite thing, and we have some end caps so that the P is equally distributed. In the last problem, when we had two members that were in series, more or less, with each other, we could add together to the deflection. But if this stays, if the integrity of the weld or whatever holds these two materials together remains, what can you say about the deflection of the aluminum jacket compared to the deflection of the steel core? Well, if you pull on it, if the steel core expands by 1 centimeter, how much is the aluminum jacket going to have to expand by? It's the same, exactly. That is exactly correct. So in this case, the deflection of 1 is equal to the deflection of 2. And so this is the idea that you would be using. Now, the other thing that we have to think about is what P is. If we put some sort of they always talk about rigid end cap, which is just a a code for saying we're going to distribute that load across the entire thing. If we pulled on that with 10 kilonewtons, for example, part of that operates, or part of that is taken up by the steel, part of it is taken up by the aluminum. So we don't know what those two parts are, but we can say that the P in the aluminum plus the P in the steel is equal to 10 kilonewtons. In other words, it's distributed in some fashion across those two. And using this equation and this equation, which we know is PL over AE, we could say P in the aluminum, for example, is equal to 10 minus P in the steel. And then we could plug that in for the aluminum, and then we would still have one equation and one unknown. So we can solve for everything that way. You have to think about the way the load is distributed. So if you have something that's acting over in its entirety, part of it's going to be borne on the steel, part of it's going to be borne on the aluminum. Okay. Anyone have any questions at this point? All right, well, that is the beginning of section 2.2. And so we will continue with that on Monday, and we'll talk about section 2.3, which is deflection caused by temperatures. And we will continue our discussion. So looks like our take-home quiz is probably going to be Friday, so you'll have it over next weekend. All right? All right, well, you guys have a great day, and we will see you Monday.